Okay, our next speaker today is a contributor talk from, well, I just asked Ahmed for his last name. I'll just call him Ahmed. So Ahmed is it's a theoretical talk on the modeling of effects of dynamic strain on magnetic structures in bismuth ferrite. Perfect. Thank you.
Well, good morning, everyone. First of all, I would like to thank the organizers for giving me the opportunity to talk about my research. My name is Omid, and everybody has a problem pronouncing my last name. I understand it completely, so everybody can go with Omid. And I work with the research group of Dr. Lauren Blaish at University of Arkansas. I'm graduating soon, so if you have an open position for postdoc, I would be happy to talk to you about that. Okay, today I will be talking about the strain-induced magnetoelectric response of BiFeO. I will be following two objectives here. First, to study the dynamical properties of BiFeO as a prototype of multiferroic materials under the influence of time-dependent magnetic fields. We are mostly focused on the temporal behavior of polarization, magnetization, strain, and more specifically, the magnetoelectric response of BiFeO within the gigahertz regime. Also, we are trying to reveal the existence of some maybe novel quasi-particles. So everybody in the audience is probably familiar with this cross-coupling. Here we are mostly focused in this area, like how to affect polarization with applying a magnetic field. This can happen in two ways. The first way is direct way. You apply magnetic field, you affect polarization. And the other one is indirect way. You apply magnetic field, you affect the strain, and then the strain affects polarization, which is the indirect way. So in order to see how polarization is affected by applying magnetic field, you can start with the expansion of free energy. And if you take the derivative of free energy with respect to electric field, you will get this. Oh, sorry for that. Here, because we are purely applying only magnetic field, we can neglect those terms having electric field involved. And we're left with the spontaneous polarization and also the linear and quadratic magnetoelectric response of the material. But it turns out in case of bismuth ferrite, if the applied magnetic field is large enough, you can also ignore the linear response in comparison with the quadratic response, which ends up like having this equation here, the spontaneous polarization as well as the quadratic response. So, but what about the role of a strain here? In order to see the role of a strain, we can start with an analytical model based on the a Hamiltonian, which is based on the expansion of the free energy again, with respect to the power terms of polarization, magnetization, and strain. So here, as you see, we got the polarization, strain, like higher powers, and then the coupling. Here we have electric field at polarization, which is assumed to be vanish here, and also the coupling terms. So if you derive the Newtonian dynamical equations here after like doing the math, you will have three different terms here. The first term here that I see, like it has the direct magnetoelectric coupling. Also, you have two other terms which involves electrostriction as well as the combination of electrostriction and magnetostriction. So Now, if you derive the equation that I showed in the previous slide, with respect to a magnetic field, because here we are interested in the quadratic response, we are supposed to apply two fields. A first magnetic field with the frequency of omega, and then a second magnetic field with the frequency of omega prime. So here, in the simulations that I will show later, we applied two magnetic fields. One of them a DC field, and the other one is an AC field with the applied frequency of omega. So if you do that, you will have two components with this quadratic magnetoelectric response. The first one is when you apply apply DC and AC field as a combination. The first component is a term that couples the DC and AC field. From now on, we call it beta 0 omega. And the one that couples AC field with itself, from now on to be called beta omega omega. So based on this model, we perform atomistic simulations using molecular dynamics. But because we are also interested in the role of strain in mediating a strain in the magnetoelectric response, we perform two types of simulation. Case one is when we clamped the strain. In this case, during the course of the simulations, we didn't allow the strain to change. And the second case is unclamped situation that strain is allowed to change during the course of the simulation. Maybe later on I call it a strain fixed or a strain relaxed in the next slides. The molecular dynamic simulations are performed within the framework of effective Hamiltonian. The supercell size is 12 by 12 by 12, and DC and AC magnetic fields are applied along the direction of weak magnetization, antiferromagnetization in the material, and we are using bulk BiFeO. So here are the results of the simulations. Here is the temporal behavior of polarization and temporal behavior of magnetization when the frequency of applied field is 160 gigahertz. First of all, as you see, polarization follows the field, which reveals the magnetoelectricity in BiFeO. Not a big surprise. But also, we see additional peaks here. First of all is the generation of a second harmonic, which is exactly twice as the frequency of applied magnetic field, but also a dual vibration of around like 4,000, 7,000 gigahertz, which are the phonon frequencies. So what about when you relax the strain or unclamp the strain? When you unclamp the strain to see the role of a strain, you will see two additional peaks over 90 gigahertz and 267 gigahertz. We have already reported these results in a PRL paper. And as you see, these two additional peaks are a combination of a mixture of optical phonons, acoustic phonons, and magnons. So we propose maybe we can call them electroacoustic magnons. But more importantly, and also I would like to mention that based on this, we could calculate the magnetoelectric response based on our model. And our calculations are in agreement with the experiment, like the value that we calculated for the magnetoelectric response beta are in agreement with the measurements of Tabares. So now back to the ME response. Let's consider the first component, which couples the AC and the DC magnetic fields. As you see, for the case of the first component, this component of ME response can go through resonances under three different circumstances. First, if the response, if the frequency of the applied magnetic fields corresponds to the frequency of a magnon, which can be seen here. Here you can see a resonance. Also, if based on this term and this term, the frequency of applied field corresponds to the frequency of optical phonon or the frequency of a strain, you will see again resonances for the case of the first component of the ME response. About the second component, which couples the AC field with itself, You have the same story with a little bit of difference. This one also goes through resonances if the magnetic susceptibility goes through resonances, or when the frequency of applied magnetic fields corresponds to the half of the frequency of the optical phonon or of the strain. So for that, we calculated the magnetoelectric response of BiFeO when we changed the frequency of applied magnetic fields from like about 20 gigahertz to 500 gigahertz. So here, the real and imaginary parts of the response are shown. In the left graph, you see the first component in solid lines and the second components in dashed lines. As you see, the second component not only goes through resonances at 90 and 267 gigahertz, but also you will see the resonances at half frequencies, which is in agreement with our analytical model. So to somehow summarize whatever I have been saying so far, you apply magnetic fields, maybe with two different frequencies, or set one of them to DC, and then you will have two frequencies. If, for example, you set one of these frequencies to 0 for DC field, you will have the resonances when these two equal to each other, or when the AC field couples with itself, you have the case of 2 omega, and this is how you can see the mediation of strain or acoustic phonons in the generation of these electroacoustic phonons. What about the case that the structure adopts domain walls, like in case of multi-domain? In that case, we studied when you have the case of 109-degree domain wall. So in this case, we performed the same simulations, but for the previous case that we had the monodomain, the supercell size was 12 by 12 by 12. But here, for the case of multi-domain, I got a supercell of 10 by 10 by 20. Here, when you calculate the ME response of the material, again, but here we could go even further. I like to up to 1300 gigahertz. When you clamp this strain, and when you unclamp this strain, you will see different situations. When you clamp this strain, these three guys, like 287, 285, 105, and 80, go away, which means that these are the so-called electroacoustic magnets that I was talking about. But either you clamp or unclamp the strain, these two peaks are still there. And the only difference between the two simulations is that this one is the case of multi-domain. So we could conclude that these two vibrations are due to the existence of the domain walls and vibrations of the domain walls. So that's why we propose to maybe call these two types of vibrations localized electromagnons. In order to investigate further the case, we performed the calculations. I calculated the magnetoelectric response not only for the whole structure, but also along each plane parallel to the domain wall. Like here, as I mentioned earlier, the supercell size is 20 by 10 by 10. So, and then the domain wall is one domain wall you see around the plane number 10, and the other one is around plane number 20. So as I mentioned earlier, you see the resonances along these frequencies like 1150 and 390. And now you can see how the response is within each domain wall. So in order to see this graph more clearly, you can see the top view of this color map. As you see, along this frequency, you will see resonances for the quadratic response. And also, you see the response is even intensified near in the vicinity of the domain walls. So to conclude, our results explain how mechanical strain leads to the formation of maybe new quasi-particles, electroacoustic magnons, or you can call the other ones localized electromagnons. And talking about the applications, maybe experimentalists can tailor the shape or the size of the sample, which ends up in changing the strain in the material. And with that, they can probably play with the resonance frequency of the material and enhance the response of the material in order to take advantage of its technological applications. And also due to the generality of that model, because for developing the analytical model, we didn't choose any specific materials. This could be maybe applied to a broad range of materials. And also, in this case, we would like to mention that dealing with such cases probably needs to be careful about the nonlinearities, nonlinear aspects of the case. And with that, I would like to thank you, and I would be happy to take questions.
Thank you very much. Questions?
Well, thank you very much. I think your resonance is absolutely clear, but what about the domain structure you put in there? I mean, when we do similar simulations, we need enormous relaxations. I mean, how did you, did you relax it for sufficiently to get the fine details you're showing? Or, I mean, how sensitive are they to your global relaxation? I mean,
well, actually, for the relaxation, in case of MD and MC simulations, I usually wait long enough to see if the structure is contained.
Well, long enough can be more than 2 years, right? I mean, it depends on... Yes.
Yeah, but in terms of like MC and MD sweeps, for example, in case of MC sweeps, I wait until like about 40,000 sweeps, which is consistent with the other structures that I've been studying. In case of MD, as long as I remember, it was like about 100,000.
Wow. Lower limit, yes. I mean, did they ever shift?
Well, we had a problem at the earliest stage of this project because when we were applying the magnetic field along one specific direction, we figured out the system is stuck in a kind of local minima. So we had to wait even more to see if the structure is...
Okay.
Yeah.
Good luck.
Yeah.
Okay, any other questions? I have a quick question. Anything special about dispersion or statistics of these quasi-particles?
Well, I didn't see anything. Maybe no, maybe I didn't consider that.
Okay, could you also comment, so Vincent was talking about spin cycloids, which would need a very large unit cell to be incorporated. So I noticed that your cells are quite...
Well, you know, the magnetic field which is applied here is above 20 Tesla, so the cycloids are all gone.
Right.
Yeah.
Okay. Yeah. Thank you very much. So let's thank Ahmed one more time. Do we have the next speaker? J.M. Liu. Huh. Right. Okay. I guess we will be taking a break.